Hello, my name is Lucia. I'm from 3D Natives, and I'm presenting you our next conference. It's from Autodesk, and the subject is improving 3D printing workflows using automation. In this occasion, our speaker will be Peter Rogers, APAC product specialist of Autodesk. Peter, welcome. Good morning.
Hey, how you going?
Peter is an additive manufacturing specialist since 2016 in Autodesk. His role entails sales, business development, and channel management in the APAC region for Autodesk. After Autodesk acquired Netfabb in 2015, he has worked hard on the GTM strategy and has been crucial in the fast growth achieved in the region. His knowledge of additive manufacturing stems from his global sales director role at Kabuku in Tokyo. His strong results fueled the company's growth, leading to a total of 10,000? Whoa. In venture capital fundraising, graduating from Swinburne University of Technology in Australia. International Business Arts double degree. Has been living in Tokyo for a total of 10 years. Whoa, that's impressive. Well, Peter, I will leave you here. Welcome, and well, I will come back with you for the questions in some minutes. Okay, enjoy your conference.
Yeah, sounds good. Thanks, Alicia. So as I have been introduced, so my name is Peter Rogers, and I look after the additive manufacturing products with Autodesk. I'm originally from Australia, but based out of Tokyo, and I head up the Asia Pacific strategy for our additive products, as well as looking at the technical specialist side of things as well. So you should be able to see my screen popping up in just a moment. So let me jump that into full present mode there. You should be able to see that now. So what we're going to be talking about today is looking at the ways that software can assist in automating some of the workflows for additive manufacturing. So looking at some of the challenges, looking at how things are done today, reviewing some of the issues and how they can be looked at with existing workflows, and then looking at really how our software, the key focus of the presentation from a software perspective will be around Netfabb. Looking at some of the potential for how that can automate the processes, and then look at the ROI calculations. So in terms of some of the issues that are affecting AM today, we've gone over quite a lot of these in previous presentations. Design is, of course, a key one. The parts coming out of the machine are only as good as the designs going into it. So understanding the capabilities, the limitations of the machines that you're using is going to be critical. Then having a look at the speed and cost, and then having a look further on at repeatability. If you're going to be taking parts to production, or if you're looking at doing mass customization, you're going to have very different properties in terms of what you're looking at for repeatability, but we're going to go into each of these in a little bit of detail. First, and very quickly, we're going to go into design, not the key topic that I'll be talking about today. I can go over this separately with you in other seminars. But looking at how DFAM can be used for part optimization. Part integration is a massive one, lightweighting is an obvious one, and improved functionality is a little bit trickier, but probably where we see a huge amount of improvements in terms of actual new products coming to market. How are companies achieving that? Again, from a software and design perspective, you can start from scratch and completely redesign the part, which is a great way to do it. If you're looking at optimizing an existing part, there is topology optimization and latticing. And if you are looking at creating from scratch a new design based on the requirements of that part, looking at generative design is a great way to do that. In terms of looking at the speed and cost and the repeatability, this is where we're going to have the key focus of the presentation. So I want to jump directly into that. So if we have a look at some of the designs that are going into the parts, people generally think of additive as, I've got the design, I'm going to send it to the machine, and it's going to come out as a functional part as is. If you have used a machine before, if you understand the workflows, you know that it's not that simple. There is a lot of conversion. There is a lot of, if you're working with existing STLs, you're going to have to be doing a lot of repair to them. There's going to be wall thickness checks. There's going to be checking if there's any internal volumes where trapped powder or resin could be, looking at packing to get the optimized ROI out of the machines, looking then further at packing, make sure that the parts are going to be evenly dispersed so that they're not influencing each other. For example, for an SLS or an HP machine, you'd also be looking at layer densities, and then you'd export to machine. You may have noticed that some of the images in here are using HP logos and using HP machines. That be quite a large aspect of the presentation, but there is also going to be some examples of how automation can be good for metal as well later on in the presentation. So if we have a look at what Netfabb does, is just so that we can have a base understanding of what the capabilities are here, is Netfabb is a workflow processor for taking the CAD to machine. So it's the bridging tool there that will do everything from importing native CAD formats to STLs to format, including slice files. It's going to then allow you to optimize the parts. If you do want to be doing topology optimization or latticing, you can then do further repair of the part. You can do packing. You can do basic CAD manipulation so that you can create, for example, a net shape if you are going to be doing post-processing. Looking at building of supports, toolpath optimization. We can simulate the actual build process for metal additive manufacturing within the software, and then you can take that directly to machine for exporting. So there are a number of different things that the software allows you to do, and these are just some of the key ones that we see as high-value functions, but there is a lot more that can be done in the software. So the reason why we need to understand this is so that we can understand what the next step, which is going to be looking at the automation, is going to be allowing us to do in terms of optimizing this workflow. So again, we're going to be looking at HP or SL this section of the presentation, and one of the things that we're going to look at is the strengths of the HP or the SLS technology is that you can pack a very large amount of, they can be 100% unique, they can be various different parts, but depending on the size, you can get packs of 300, 500 from parts in one machine. So this is a very, very high value proposition for companies that are doing very large different volumes of parts. But again, because of this process, it means that there is a lot more time in preparing the data. So while the machine can handle a huge range of variety, the person that's engineering these parts and the person that's then going to be processing these parts to get them ready for the machine, it's going to be a very long process for that person to actually create the pack to go into that machine. So some of the things that we're looking at and some of the hurdles that we're seeing for different companies is companies that are looking at doing mass production. They're looking for repeatability, cost, and scale. So again, looking at repeatability, they want to know that the part that they created and tested in one machine is going to come out the same in different machines. They don't want to have a variety of different results coming out of the machines because that would reduce the ability for that part to scale. If we have a look at some of the costs, again, they want to make sure that the costs that are going into the part are reduced as much as possible to make additive a suitable manufacturing technology for that part, and then hopefully to extend that out to other areas within the business so that they can leverage the technology across other functions within that company. And then, of course, looking at scale. So if they want to be implementing this on a global standard, for example, like what we heard from Flex, they've got various different facilities across the world. And if they want to have a standardized process, then they definitely need to have a process that is leverageable within each of the different facilities. So that includes making sure that you have a very systematic approach to the way that you're applying different methodologies to the build. And that is something that's really only going to be achievable if it is not based on individual siloed people, So you can't have the exact same person until we figure out cloning, until we understand the way that that person is working on each of the parts. So if we can have a very logical approach to the way that the parts are prepared, standardize that, and then have that scaled across all of the facilities, then we start to see a real expansion of the additive ability to scale across those different parts as well as regions. And if we see the three words that have changed across the top, the hurdles in high variety manufacturing, again, this is mostly looking at service bureaus and also looking at companies that have a very, very large volume of parts that could be, for example, spare parts that are going to be manufactured on a once-off basis or very small lot basis. These guys are going to be more focused on looking at speed, cost, and scale. If you're going to be manually preparing each of the individual pieces of data, that can cause the speed of preparation time to go up. The cost, of course, is going to go up in relatively limited cost of labor, but you're also then going to have a look at scale in terms of new designs, the ability to take on new work, working within multi-machine environments, and the engineers do have their limits of how much work they can do within one day. So having a look at these three categories is going to be highly influential for high variety manufacturing. So when we are looking at the way that automation can assist with these things, it's going to be, the way that I like to think about it is looking at how you can apply the know-how and best practices, put it into a script, and make it a repeatable process for all of the different machines that you're running across the business. So some of the things that we could look at as a workflow example would be looking at importing an entire folder of parts, doing wall thickness checks, and then saving the parts whether they fail or pass that criteria that you've set up within the wall thickness check, and then passing on those print files to a 3D packer, which will then prepare that module for you so that you don't really have to do much manual work, especially considering a lot of these processes are very, very tedious. They're doing the same thing multiple times, so it can be a bit of a bore for the engineers that have to do them. So very quickly, just to have a look at a video that's doing this. So what we're going to be doing is Lua scripting language. So Lua scripting is what we're going to be running here. We're going to be setting it up as a script that's going to be bringing in parts, checking the wall thickness, and separating. So it's going to filter it so that the engineer knows which parts to look at, and this is going to really help them be as optimal with their time. So what we're going to be doing is it's a fully customizable script, as you can see there. We've got a pop-up window which can also be customized for separating the parts, doing a tessellation. We've got the wall thickness threshold, and then what we can do is bring all of the parts from that individual folder. So we're going to remove all the parts that are in the failed and pass folders. And then what we're going to be doing is from the files folder, there is one part within this that is going to be causing issues. As you can see here, we have some parts that are STLs, some that are 3D, 3MF formats. We also have some native CAD formats. So it's going to bring in a huge range of different parts into that one build. What it's going to do then is it's going to check to see if it's 0.5 mil being met. As you can see, this part is 0.2, so it's not going to be meeting the criteria. When we run this script, it's going to upload all of those parts into the Netfabb environment. It's going to be doing a thickness check. And as you can see, the part that was going to be failing as expected is filtered. So instead of having to check all of these different meshes, which is going to be, I think it was close to 100 parts here, the engineer only needs to look at one part, which really makes them efficient with their workflows. But when we are having a look at this kind of thing, it is a great tool, and having a look at the Lua scripting is a great capability. You can edit these sort of things here when you are building out that capability and when you do want that flexibility of editing on the flow. So once you understand that workflow and once you have these parameters set up, what you can then do is set these as presets so that this screen doesn't even come up at all, and it's just going to run that script on all of the parts that you are looking at doing. However, one of the things that we do find is that you do need to go into the software, click Run Script, and then click that script. Again, it's not a massive amount of work compared to what people would be traditionally doing, but it is one thing that if you were looking at having a 24/7 backend server running where it's going and doing this on a as-need basis, for example, someone loads a bit of data up onto your server, this is going to be a pain because you do need to have that manual intervention. So what we're looking at doing is we have a very open platform, which we have uploaded to GitHub, so you can actually see all of the information. It's very open. You can adjust it, you can edit it, you can do what you want with it when implementing. It's called Netfabb Application Server. And what it is, it's a RESting API that is going to connect your service to Netfabb. So instead of going in and manually clicking the Lua script's execution, what you can do is you can have this automatically done based on the connection to your system. Again, very easy to use. It's open source. Jump on it. If you go into Google and you type GitHub Netfabb Application Server, you should be able to find it very easily. So what does it actually allow companies to do? So for example, this is one way that you can look at how it's being used by, for example, here you've got the manufacturing server. It could be that the manufacturer has a website, for example, a service bureau where designers can upload their parts to be sent for manufacturing. What you can actually do is within manufacturer server, you can upload the parts and have them available from the designer. The backend will then automatically call using Netfabb Application Server. Netfabb, it will open it, it will run scripts in the background so that there is no human intervention at all. The individual manual clicking of the Lua script technology is not required. And then once that has done, the scripts will run in the background. And the workflow will then have an output that will be derived again from what you're requiring it through the scripting. And that will go back to the manufacturer server where you can either send it back to the designer for confirmation of parts that don't meet minimum criteria, or it could go straight through to print so that you are having that workflow nice and smooth. So one way that we can look at it is, for example, the designer uploads to the server. Based on that server's preparation, you're going to do all of the printability checks, the error repair, the build setting fine-tuning. If you need to do it, you could do labeling for serial production, build preparation, and then documentation, which will then go through to the printer. If we are looking at, for example, a design that has sent a part that does not meet the minimum criteria and it cannot be fixed by base repair, and you do need to confirm with the customer, you can send that part back to the designer so that they can do a manual check and then get back with the part that can then actually printing. So one of our customers in Japan that has actually implemented this very effectively, this is an automated report that is created through the scripting for Netfabb. And what this is looking at doing is it's pulling in the STL that a customer has uploaded. It's looking at the individual areas within this part, critiquing it. It's checking, for example, in this case, they've got a minimum wall thickness criteria of 0.8 mil. And as you can see, it's actually automatically created this, which is a 3MF file format. It has highlighted all of the areas that are not meeting the criteria of 0.8 min wall thickness, and it has applied a red surface to each of the areas that has issues. What it can then do is it's also pulling all of the information about that STL. It has all of the information that can then be sent back to the customer, and it's saying, is this going to be acceptable? Do you understand these risks that some of these areas might be damaged during the build? So that helps to reduce the risk of that manufacturer producing this part and having failure. If there are areas that can be automatically fixed, they will be automatically fixed. But again, that comes down to the way that the script is customized. Some of the other things that we can have a look at is, for example, a build prep packing that is based on adjusted setup exactly for the way that you guys want it done. And that can all be done within this Lua script as well. So what we're going to be looking at doing here is you can set up an area of the build tray for very large parts. This really helps to reduce the distortion of the large parts if you put them in the center and at the base. Based on that, once you have those parts locked in, it's going to fill it with medium-sized parts. And then once you have those medium-sized parts locked in, it's then going to bring in the small parts. So as you can see, all of these parts in there, it's then doing a complex calculation for the smaller parts. It's got the information about the build density. And one of the things that I quite like about this is that you can actually set up and change and adjust all of the information about the way that this is done based on the parts that you're making, the the know-how that you guys have, and you're not relying on software providers to provide you the best solution. Of course, we do have a very, very great setup in terms of automatic packing capabilities, but if you did want to adjust it, or if you're creating a new machine and you want to be building out best practices, this is a great way to actually identify and create these methods. Talking about plastics mostly until now, but one of the things that we are seeing quite a growing interest in terms of metal is looking at orientation and support optimization. And what we're going to be doing with this script is taking in this part, applying various different orientations, applying various different support strategies, simulating it so that we can then see which is going to be the most effective way of us making that part. So one of the things that I always like to do with people when we do have this conversation is to look at, these are the 4 different orientations. Which one would you decide if you were running a machine? It is a trick question because there is no such thing as an answer that meets every single criteria. But when we have a look at the workflow, I want to just show you and focus on the way that Lua is being leveraged to set this up. So what we do is within the simulation, we have the preparation that goes on in terms of creating the build plate, setting all of the information about how the build is going to be running, and it's going to create these input files. We have the input files in terms of how that build is going to happen. We just need to bring in the 3MF format of the part and the supports. So based on this, what we're going to do is we're going to repair that part. We're going to do orientation. We're going to do support generation based on scripts that have already been pre-set up. And then we're going to export that to simulation for automatic simulation knock-on processes. So this, again, this process has taken 23 seconds for us to do that. We've got this output file, which is going to be the orientation and supports, as you can see here. And then that is going to have an out file, which is the simulated results file. Then open up, manually look at how the distortion is happening, how the residual stresses are building up, and whether that orientation and support method is going to be suitable for the build. So if we have a look, again, we have 1, 2, 3, 4, and taking the guesswork out of it, we can actually see what that looks like in terms of distortion on that build orientation. But then we can also take it so that we have a look at how many parts can fit into that build. How much support volume are we having? What is the build time? So we can have a really, really educated and scientific approach to the way that these parts are going to be prepared. Jumping into what it looks like in terms of ROI, we are running short on time. So before one of the team jumps in and lets me know that, I wanted to address that. But if we are looking at the speed and the costings of this, again, automation is a great way to keep it relatively flat in terms of taking on new orders without having to have too much cost integrated with that preparation. So if we have a look, this is the manual preparation. Of course, you don't have the overheads of the software, which are going to be a little bit higher than if you were doing it on a one-part basis with an individual engineer. But as you see, the cost of preparing more parts hits a threshold. You're going to have to do a new hire. You're going to have to then go and do the manual processing there as well. So there are a lot of knock-on effects of having a manual process. The other thing is, once you've hired that second person, once you reach that 2-person threshold and you're looking at getting a new machine, you're looking at taking on new, you might hit the point where you've actually hit the capacity and you can't take on new projects. This is, of course, going to be a challenge. So automation really helps to take out that requirement. If we have a look at the amount of parts that an individual can take on within automation, it definitely improves. So I definitely think that there is a lot of value here. If we start to look a little bit more complexly at the ROI calculations, again, I don't want to go into this in too much detail, but there is a bit more explanation in here. If we do have a look at, for example, a service bureau that has on average 100 parts coming through per day, and even though all of the parts aren't going to be completely unique, on average, they would look at about 6 minutes per part to prepare. If their engineers are paid $60,000 or $30 per working hour, we would look at the the calculation below. The overall ROI in this situation of somebody that is implementing this would be looking at around $55,000 in savings, or around 375% ROI based on a very, very rough estimation of $20,000 in software and servicing for a license that would allow them to achieve this. Of course, that is one example, but if we have a look at the constraints of part number, for example, 100 parts, wages being $30 per hour, how fast would they need to be in order to break even? And again, if it takes them more than 3 minutes, they're going to be hitting ROI very quickly. But the other thing is, this is again based on 100 parts, 200, 300 parts, then you're starting to see even more ROI derived from that automation. Again, then looking at part variables, if you do have, for example, a constant 6 minutes per part and wages are steady, the amount of parts that you would need to hit ROI is looking at about 60. And again, based on wages, depending on where you have facilities, the wages might be quite different. Setting it at 0, just in case we do have some education facilities on here that are looking at, teaching their students, and they can get away with having a bit more cheaper labor going on there. Then the wage based on 6-minute preparation and 100 parts hitting parity at around less than $15. So again, basic ROI calculations are very achievable with this. But the thing that we need to know, not just about direct ROI, there is also a lot of non-direct ROI that is going to be allowing people to get knock-on benefits. Not going to go over all of these, but some of them are looking at standardization of processes, which really helps with a very, very large topic that we've been discussing over the last few hours, which is certification. Having a look at reduced costs, which then can hopefully be passed on to customers, which can then hopefully then, again, allow for increased demand of parts, which then allows further investment in machines and hopefully allows for companies to actually start a bit more seriously. Some of the other ones, easy to further scale businesses, faster and easier onboarding of new staff is a massive one that we're seeing as a very surprising non-direct ROI, because the standardization is already done. They very much have a process that they don't really need to understand all of the specifics, but they still can leverage this tool. And the other thing is that it's also somewhat interesting is that the amount of time that's spent on labor-intensive, very tedious tasks is highly reduced, which means that the work environment and the increased retention of staff goes up. And happy workforce is something that I think everyone's trying to achieve. And if we can reduce the amount of times that they're going in and measuring walls, then that's great. So again, I'm not going to go over all of these. I would prefer to jump into some of the QA if we do have any. So I would like to wrap it up there, but I will leave this up on the screen just so that people can read through it as we go through the QA as well.
Okay. Hello, Peter. I'm back. Thank you very much for this interesting presentation. I actually do have some questions for you. Okay. The first one, the most voted one, is does the scripting need to be done from scratch, or the software records macro that can be used as a script to change the variables?
Yeah, absolutely. So all of the information that is in the script has various different tools, and it has various different example scripts. So you can actually go in. There is a very, very large range of functionalities that can be done within the example scripts. If you are looking at creating something that's a little bit more intense, which, for example, connecting in with your individual servers, connecting in with CRMs, that is a very, very much a workflow. So that can be somewhat challenging. Luckily, for those that are already using Link 3D, we do have integration with Link 3D, which was presented earlier in the marathon. So that means that you can, for example, already have quite a lot of this done, and the ability to then use the scripts to feed back into Link 3D is something that we are working on as well further. So there is current existing, easy to access, but the flexibility to then expand that out is something that is also something that we have seen a lot of success with.
Great. I have another. Yeah, I have another question. I think will be the last.
Yeah.
Also, don't forget that Autodesk and Peter, you will be in the table 4.11 if it's correct.
That's correct.
So for the other questions, I think they can go and and go straight to your table and ask you. The other one is 3MF or STL and why?
STL or 3MF? Is that the question?
Yeah.
So basic practice, which I always like to live by, is avoid STL where possible. Thank you to Entopology for this amazing sticker. I think that there is a death to STL hashtag that's going around. To be honest, it's an incredibly tricky file format to work with. It loses instantly the parametric connection to the CAD format. It's very difficult to work with in terms of editing. We are 100%, I mean, we're Autodesk, which is AutoCAD, which is focused on working within the CAD environment. So we would prefer not to have any mesh formats at all. Where required, we are 100% behind 3MF. It's an incredibly flexible file format. It captures a lot of metadata. It's very intuitive in the way that it can be integrated with different systems. And as you saw with this, 3MF is already integrated with Microsoft. So it's being pushed by a lot of different other softwares, so that it's not just an additive format, but it's a 3D visualization tool that can be used with Adobe. It can be used with Microsoft. It's the key it's the key file format that we're seeing a lot of success with. Anything that's full color should be 3MF. If it's not, it's being inefficient. Anything that is looking at multi-material and having metadata around the material that's going into each of the different sections of the design, that should be 3MF. As a rule of thumb, anywhere that we can avoid STL and go with 3MF, we do. It also helps to reduce the file size, which is massive when you're working with very complex geometries as well as lattices. So if you haven't had a chance to play with 3MF, check it out. If you want to know more, again, room 411, feel free to come and have a chat with me about it.
Great. Thank you very much, Peter. See you around, and please enjoy them.
Always a pleasure.
Yeah. Bye.
Thanks, guys.